Chapter 14, Energy Method, Strain Energy in Beams. Let's solve another example in strain energy. So if we have a two fixed support beam handling a concentrated load and connected to each other, two part of the beam connected at somewhere in the middle by a pin, and the concentrated load applies at the pin too. So if the width of below beam is constant, from A to C, so all over the span, all over the entire cross section, the width remains the same and it's B. Mhm. And the strain energy of two part of the beam, so this is strain energy of part AB and this is strain energy of part BC, and they are equal to each other, mhm, based on the problem statement assumption. Then we want to calculate the ratio of height of two parts. So we want to know what is the ratio between the height of two section. Mhm. So if this is part AB with the height of HB and width of B, the same for the other part, we do have HBC and again the same widths of BC. So we do know the widths of two part are identical or equal to each other. We want to know what the ratio of their height is. So we are looking for height of AB uh, over height of BC. And the length of the first part is 2L and the other part BC is just L. So first, by consistency of deformation, we do know that the location of load is just going a downward movement by delta B, and it because of the consistency of deformation, it doesn't matter if it's delta B left or right. So in either side, it's the same due to consistency of, and so that means delta B L is equal to delta B right, and that's delta B. Mhm. So that's the delta B at the two sides of the pin are equal to each other, and both of them are delta B. And also, if you remember from when a force applied to a spring, mhm, so delta is F over K. Mhm. How that goes, if you pull a spring with the stiffness of K, it moves by delta, and that delta, that deformation, is force over stiffness of a spring or beam. So FAB, if we can simulate our beam with a spring, force at AB over K, stiffness at AB is equal to delta B left, and that's equal to force at BC over force stiffness of BC. And if we call this equation 1, and again based off P delta, mhm, strain energy is area under force displacement. So U is a half of area of this triangle is a half of P times delta, P times delta. Mhm. And again in a spring, if we can just replace delta in the strain energy formula, it just says U, or strain energy is equal to force squared over 2 stiffness. Mhm. So let's apply the strain energy, which is the same at the two parts due to problem statement. UAB, U for the first part, UAB is equal to force AB squared over 2 times the stiffness of AB, and that is equal to, based off problem statements, equal to UBC. This is UBC, and that's equal to FBC squared over 2KBC. Then if these two are equal to each other, then f squared of each of them over 2k are equal to each other. And one can easily say, if you just bring this down here and 2k over here, one can say f squared ab over f squared bc is equal to the ratio of their stiffness. If we call this equation 2, from equation 1 we have a consistency, so delta b left is equal to delta b right. So FAB over KAB, if we just rearrange this based on force, so we take FBC down here and again this up here, FAB over FBC is equal to the ratio of their stiffness, and if we raise the whole to the power of 2, so if we raise it to the power of 2, we can get this equation. Based on 2f squared AB over f squared BC is equal to the ratio of their stiffness, based on equation 2, and based off what we derivate from equation 1 and raise it to the power of 2, it just says f squared AB over f squared BC is equal to the ratio of k squared AB over k squared BC. So if both of these two are equal to f squared, so it means these two are equal to each other. So if k squared over k squared ab over k squared bc is equal to k, so we can cancel out one of them. So it just says the ratio of their stiffness should be 1, because it just simplified by 1, and that if we know that the ratio of the stiffness are equal to 1, then we can move on and just say, for example, consider part A like as a cantilever beam. So in that sense, KAB delta at B is PL, not P. FAB L cubed 2L cubed over a 3EI. So one can say K is 3EI over 2L cubed for the first beam, and do the same for the other one, and it just gives you delta BC. So KAB is equal to the stiffness of AB is just a 3EI over of 3EI of AB over 2L cubed, the length to the power of 3. And that's equal to KBC, which is just a 3EIBC over L cubed. And if these two are equal to each other, it just says their ratio of their stiffness are equal to each other. So in terms of formula, so that's a reach to this equation, a 3EIB over 2L cubed is equal to 3 times EIBC over L cubed. And if you simplify that equation, it just says moment of inertia of AB over moment of inertia of BC is equal to 8. And we do know moment of inertia is a for a rectangular cross section is 1/12 base cube height, one's with the height of AB and the other with the height of BC. So if you simplify the equation, it just gives you HAB is equal to 2 of HBC. And we were looking for the height of each part. So it simply says if B remains the same, but HAB is equal to to HPC. Mhm. Thank you. We'll solve more problems.